Okay guys, so this is constructing redox equations part 2. Part 1 was doing it using ionic half equations. That's pretty easy. This is the much harder way of doing it using oxidation states, and it's when you don't know the ionic half equation. It'll be obvious when to do which one. And there's 4 steps to this, although the 4th step is a bit weird in that you have a choice of 1 or possibly 2 of 3 things to do. I'll get to that in a bit. So first of all, we've got our question, and let's say the question is as follows. Hi is oxidized to I2 by H2SO4, which is reduced to H2S. So that's my question. And what it's asking me is to make a balanced redox equation from that information. So my equation for this reaction. So the first thing I do is I use the information given to construct an unbalanced equation. And this equation will definitely not be balanced. That's fine. That does not matter yet. We'll balance it out later. So let's see what I've got. It says Hi is oxidized to I2. So I'm going to have my Hi on this side, I2 on that side, by H2SO4, which is reduced to H2S. So I've used the information given, and that's a pretty small question I put up there. In the exam, they might hide that information in like a paragraph of text, so you have to be really careful to pick out which bits are actually reacting. But that's what's reacting, so that's my equation unbalanced. The next thing I need to do is I need to find out what has been oxidized and what has been reduced, and by how much. So we can use those 5 simple rules. Oxygen always has an oxidation state of -2. Fluorine is -1, hydrogen is +1, an uncombined element is 0, and that includes diatomic elements. For example, I2, that is still an element, because it's only one type of atom, and anything with a charge has an oxidation state equal to that charge. So I'm going to use those rules on here. So my hydrogen is +1, each of these hydrogens is +1, each of these oxygens is -2, that's going to be 0, and we've got +1 there. From those 5 rules, you should be able to figure out the oxidation state of everything else, because the oxidation state of everything in this molecule equals its charge. And the charge of this molecule is 0. Look, there's no charge there. If there was, there'd be a plus or a minus. There isn't, so this has to equal a total of 0. So if H is +1, to equal 0, iodine must be -1. I've got 4 oxygens, each at -2, that's -8, +2 for my hydrogen, so -8 + 2 is -6, so to equal 0, sulfur must be +6. Again, that's 0, so we know all that is 0, and if each of these hydrogens is +1, that gives me a total of +2. It needs to equal a total of 0, because look, there's no charge here, so my sulfur must be -2. So from that, what I can do is I can see what has been oxidized and what has been reduced. And it's quite obvious, my iodine has gone from -1 to 0, and my sulfur has gone from, let's do it at the top, from +6 to -2. What we then need to do is look at the difference in these oxidation states. So my iodine has changed by 1, because the difference between 0 and -1 is 1. My sulfur has gone from +6 to -2, so that is a difference of 8. Okay, so that's step 2, find the changes in oxidation state for your reaction. Step 3, we need to balance the oxidation states using our molar ratios, our big numbers in our equation. So my sulfur has changed by an oxidation number of 8, my iodine has only changed by an oxidation number of 1. I need this to equal 8. So what I need is 8 iodines changing. Because 1 molecule changing by 8 is the same as 8 molecules changing by 1. So all I'm going to do is I'm going to put an 8 here, changing my molar ratios. But don't forget, we have to balance out my iodines on the other side as well. So if I've got 8 iodines here, because that's what's changing, I also need 8 here. So that's 4I2, because 4 times 2 is 8. So that's step 3, I would balance the oxidation states using my molar ratios. Now it gets a little bit weird, because it depends what type of reaction you're doing. Usually, the vast majority of the time, we then balance out the oxygens by adding water to one side. So if I look at this equation here, I've got 4 oxygens on this side and 0 oxygens on this side. So I'm just going to rewrite this equation out in step 3. So 8Hi plus H2SO4 goes to I2 plus H2S. 4 oxygens on that side, 0 oxygens, right? 0 oxygens on this side, therefore this side needs 4 more oxygens, so I add 4 H2Os. Okay? Also, as part of step 4, you may have to add hydrogens, H pluses, to one side to balance out the hydrogens. Now, in this equation, I don't need to do that because I have a total of 8 add 2, 10 hydrogens here. 4 times 2 is 8, add 2, 10 hydrogens there. So my hydrogens are already balanced. If it turns out, you do need to check, if it turns out your hydrogens aren't balanced, add a certain amount of H pluses to one side to balance that. Now you can only do that if you're using an acidic solution to supply the H pluses, because remember, acids release H plus. So if you haven't got an acidic solution, you can't do that and you've gone wrong somewhere. Also, if you're using an alkali solution, you may have to balance the hydrogens and the oxygens with an OH minus. So there's kind of 3 ways to go about that. I would always first try and do it using waters. If not, then think about adding hydrogens or OH minuses. And that is my final balanced equation. What I'm going to do now is I'm going to rub this off just like I did with part 1 for balanced and redox equations. I'm going to rub this off, put another question up, and if I was you, I would pause it, have a go at it, and then once you've got an answer, play it again and see if you've got it right. So, here's my question. MnO4 minus is reduced to Mn2 plus, whilst Fb2 plus is oxidized to Fe3 plus. So, pause it now. Have a go at it, and then press play when you feel you've got an answer. Okay? So here's what I would do. So first of all, let's write our equation. Step 1, our unbalanced equation. So I'm going to have MnO4 minus and iron 2 plus, and that is going to go to Mn2 plus plus Fe3 plus. So I've just picked out the information from the question and put it into an unbalanced equation. Remember, it's going to be a little bit more hard in your exam, so do get a bit of practice at doing that. I then, step 2, need to do all of my oxidation numbers. Now, just to speed it up, I'm going to cheat and use my sheet here. What you'll end up with is Mn is plus 7, oxygens minus 2, obviously that's plus 2, because you've got a charge of plus 2, again plus 2 and plus 3. So that's all my oxidation numbers. Let's look at what's been oxidized and what's been reduced. Well, my manganese has gone from plus 7 to plus 2, so that's a difference of 5, and my iron has gone from plus 2 to plus 3, so that's a difference of 1. So my manganate has changed by 5 times as much as my iron, so what I need to do is balance that out by making 5 ions. So step 3, I'm going to balance my oxidation states by my molar ratios, by using my big numbers. So MnO4 minus plus 5 Fe2 plus. That way I've got this 1 5 times. 1 times 5 is 5, which is the same as 5 times 1. And that's going to go to Mn2 plus plus 5 Fe3 plus. Because don't forget, it has to be balanced on both sides of the equation. So that's step 3 done. Step 4. I then need to try and balance out my oxygens and my hydrogens. Remember, always try and start with water. Do the waters first. So I've got 4 oxygens on this side, no oxygens on this side. I must need to add 4 waters here. So MnO4 minus plus 5 Fe2 plus goes to Mn2 plus plus 5 Fe3 plus 4 H2O. That's my oxygens balanced. When you're doing that, don't worry about the hydrogens. We can balance those later if they need to be balanced with our H pluses if it's an acidic solution. So let's look at our H pluses now. I've got no H's on this side, and I've got 8 H's on this side. This would be done in an acidic solution. We use sulfuric acid for this, and not hydrochloric acid because it produces chlorine gas and kills us, which is frowned upon. So I need to add 8 H pluses to this side. So I've got my MnO4- plus 5 Fe2 plus 8 H plus goes to Mn2 plus 5 Fe3 plus 4 H2O, and that's a mouthful. And this equation here is definitely worth learning. In particular, the 5:1 molar ratio between manganate and iron, because you're going to do a lot of moles titrations to do with this equation here. And that is how we balance redox equations using oxidation numbers.